Hi, in this video we will explore pooling, a technique that reduces the size of feature maps and the number of parameters in neural networks. This presentation covers max, min, and global pooling operations. We're going to see how these operations work in practice. So what we see here is a network that processes 32 times 32 RGB images through two convolutional blocks. Each block contains 2D convolutions, a ReLU activation, and something called max pool 2D layers. The first convolution expands 3 input channels to 16 feature maps. It creates 16 images. This is what we see in the diagram. This input image turning into like this fat stack. This fat stack represents 16 feature maps. The second convolution expands this to an even fatter stack of 32 feature maps. The max pooling 2D with a stride 2 reduces the spatial dimensions by half after each convolution. After 2 convolution operations, the 32 times 32 input becomes 8 times 8 pixels. Then we do a flattening call to convert these 32 feature maps of size 8 times 8 into a 2048 dimensional vector. 3 dense layers progressively reduce the dimensions to classify images into 10 categories. The schematic shows how the feature learning happens, followed by the classification stage that we're doing with multi-layer perceptron, as we saw before. Max pooling selects the highest value in each window. What it does is that it's just going to pick the pixel that has the highest intensity. And we see in the image that this preserves edges and prominent features while reducing by half the spatial dimensions. This operation creates a sparse representation that keeps only the strongest activations. Then we have this min pooling operation that just computes the average in those 2x2 windows. The output is smoother looking than max pooling because it considers all of the values. The image here shows the min pooling being applied to our photograph of cats, and we see that this preserves a lot of the background information and creates a blurred but also continuous feature map. This operation works quite well for textures and basically everything that we would like to compress in our images. We have a third operation that is called global pooling. This one is going to convert the feature maps into fixed length vectors. So it's going to take, for example, a whole image that could have 100 different values, and it's going to compress it into a single value. If we do adaptive max pool 2D, we're going to take the maximum value of this 100 pixel image. If we do adaptive min pooling, we're going to take the mean value of this 100 pixel image. So if we have this on feature maps that are very reduced, like what we see at the end of the convolutional layers, like for example having a 7 times 7 feature map, and we have like 1,000 of them or 512 of them, what we can do is that we call these operations and then we concatenate both of them to create a smaller vector that is going to represent a lot of the information that we have in the image. It's a lossy compression, but it's keeping a lot of important information. The red circle that we see in the diagram shows where we're going to be doing global pooling instead of a flattening operation that we saw before. So this network modifies the previous architecture by replacing the flattening layer, and this is something that would allow us to train the model while using less parameters. This is also something that will probably help us against overfitting. We need to experiment with this on our particular dataset, and this technique is very common in modern architectures like ResNet to prevent overfitting. So this is something that we're going to explore more in the practical section of this particular course. We're going to see more of this downsampling of images with adaptive global pooling when we do a lot of the experiments related to interpretability of models. There is a very powerful technique called class activation mapping that depends on this global pooling. So to wrap up, we covered the three types of pooling operations. We have max pooling, capturing feature activations that are the maximum value, min pooling having the average, and global pooling being this thing that we use to convert feature maps into compact vectors. Each of these operations has a distinct purpose in neural networks. Max and min pooling reduce the spatial dimensions while preserving important features, and global pooling creates fixed size representations regardless of the input dimensions. This helps us reduce the number of parameters in the model. The choice of pooling depends on the task requirements and the computational constraints that we have.